So how many of y'all know anything or some about CXL? So good bit. All right, cool. So when I was asked to do this, I noticed a lot of people, especially in SNIA, did not have any real background in computational storage, in NVMe. Try 3 in CXL. So when I decided is I was going to do kind of a CXL overview and kind of some of its evolution, and then kind of talk about a couple use cases for CXL that kind of come. So it's a pretty high level, and obviously because of time constraints, it's going to not focus deeply on a lot of the mechanics. So about me, I'm a technologist in DE at Dell. I've been there about 25 years. I've done standards for over 20 years. That's how I know probably about half the room from doing T10, SATA. I was kind of on the original ones in NVMe with Tom Pratt. He was there too a long time ago. CXL, and then I've done a couple SNIA twigs like CDMI, and there was a couple other I did. I'm currently one of the co-chairs of the protocol working group. At Dell, I currently focus on Gen AI solutions now, since Gen AI, if you're not working on it, then something's wrong. So, all right, so I do a lot of that, and then I'm also do CXL standards. And then lastly, last year or this year, this is my first year being an empty nester, so that's kind of been an interesting transition for me. So, all right, so let's start with CXL 1.1, right? So it's based on Gen 5 electricals. It uses a thing called the alternate protocol negotiation that allows it to switch between doing at least the root port between acting as a PCIe route or doing a CXL route. And that's done during kind of the link training. It communicates using flits, which contain these things called slots. What is a flit? Well, it's not actually ever defined in CXL. I assume it's like flow unit or flow control unit is what it means, but they don't actually define it. And the flit is kind of what's used as the fundamental communication, I guess call it packet, that goes between on a link. And those contain slots. And a slot is kind of like a fixed format size. They have two kind of slots. They have header slots and they have generic slots. I think one's like ends up being like 12 bytes and the other ones end up being 16 bytes. And that is kind of what the actual content of CXL goes into. As I'll talk about the different protocols, they actually go into the slots. Now, flits are not kind of an end-to-end routed thing. So even when we get to CXL2 and CXL3, when we're talking about flits actually only operate from the link, so point to point on the link. And like I said, these slots carry the request, the responses, the data, and then some control. And these slots are kind of fixed structured. And what I mean by that is you have generic slots and you have kind of generic slots defined G0 through, I think it's about G7 or G8. And within that slot, there's actually a fixed structure of what it contains. So it's not like, it's like preset commands or preset responses or things. So it's like, it could be, let me kind of give you an example. Like an H or a G1 slot may contain 2 .mem requests plus 2 .cache responses. So they're really fixed structured, and what slot gets used is actually done really at the hardware, depending on what it's trying to send, what it's trying to request. They have these kind of things that that control how they pack the slots, and those are actually the things that actually choose what slot gets picked or what slot format gets picked in order to do this. So that's all done at the hardware level. Does that all make sense? So CXL is comprised of essentially 3 protocols, and these end up being muxed on the link. And although the way it reads, it says they're all muxed on the link, the reality is because of these, we talked about these slots and stuff, it's actually PCI gets muxed on the link with then cache mem. Right? Because there's no separation from .cache and .mem from a perspective of where the muxing occurs at the RMUX. So it's either a TLP slot or something oriented with PCIe, or it's CXL. And that's kind of the way it works. So then we have these kind of three protocols, those being .mem, and that is for reading and writing from device exposed memory. And then there's .cache, and .cache is kind of the other direction, and that allows the device to participate with the system's coherency. So it can now, you know, own, I don't want to use the word own, but it can interact with memory. It can cache you know, memory address and stuff like that. And then lastly, there's PCI, which is the .io. And for CXL 1.1, it was direct attached only. So then this is the chart that everyone includes, and there's a lot of stuff on it. But in CXL, there's kind of three conceptual device types, type 1, type 2, and type 3. And the idea is these are really like caching devices or accelerators. These are accelerators with memory, and these are memory buffers. So this is kind of the what you're seeing a lot today of all the initial products are really around memory buffers, memory expansion, allowing you to add additional memory to systems that's not on the DDR bus. Instead, it's on this bus. But it still kind of conceptually does the load store action, right? So as you'll see in these different device types, they require different types of CXL protocols, those being CXL.io, CXL.cache, CXL.mem. CXL.io, you'll see, is across all of them. That's because that is required and is used to do kind of the configuration of the device, the discovery device, because it follows a lot of the same PCIe kind of constructs. It actually is using CXL.io, so it is using PCIe for discovery, a lot of the air handling and stuff like that. Then we have type 1 includes .cache, because the whole thing is it really wants to interact with the processor cache and be able to kind of temporarily own cache lines or have cache lines that are being modified by it, and so it has .cache. And then this actually came later, which is having the capability to do .mem to go out to talk to something else, but that was never in CXL1. It's actually like a 3.0 thing. And then we have the type 2 device. So the type 2 device is like this, but it also has memory attached. Now, the one thing I want to say is memory that's exposed through this kind of HDM range is actually, when you expose memory through CXL, it's through an HDM, or host device memory range decoder. And that memory ends up being owned by the host, right? So even though it's on the accelerator, technically the host owns this memory. That gets exposed. You can have private memory and do whatever you want. And essentially it has to use cache protocol in order to interact with that own memory that's really its, right? Because it is not the true owner of the memory from a perspective of the host. So that's really what .cache is used for in this model, is to allow me, and think in the future computational storage device, to write to my own memory that I've exposed. And this has changed a little bit as we've added this thing called HDM-DB, which I'll talk about in a little while. And then lastly, we have memory buffers, and this is kind of the simplest case. This is kind of what most of if you see CXL 1 or 1.1 devices, they're going to be these devices. And they, again, started out as this HDM-H memory, which means, and these got added actually later, the -H, the -DB, and the -D, which was really talking about, and it kind of goes to the generations of CXL, why they got added. So this is like host memory, this D means kind of device member, and DB, and I don't actually know what DB means. I assume it has to do with back and validate, but I don't actually know what the acronym is, to be honest. So those are kind of the three, and you'll see things kind of changed over time. So this is kind of the history. The only thing I really wanted to point out here is they had a pretty fast cadence, but you'll see from 3.0 to 3.1, there's a pretty big gap. And a lot of this has to do with the stuff they added, and a lot of it has to do with, I don't think 6.0, 3.0 was ready. We added things kind of on the hardware side, but we didn't have the management structures to actually use it. So we added, and there was some value to that in that vendors could start building the hardware and put the channels, so CXL uses a lot of concepts of channels, directional channels for its .mem, .cache flows and response flows. So it was good that we put it there and the hardware was baked, but a lot of the management side of it, of how you use it, was not in there. And most of those management things end up being software. So that's why it took a while to get CXL 3.1 in. So in 2.0, so remember 1.1 was direct attached only. So in 2.0, we added kind of the single layer switches. So now you can think, I have a single layer switch. I can do concepts like memory fan out, right? So I can have my root, a switch, and a bunch of memory drives. Think, you do this today with NVMe sometimes. If you don't attach to direct, you have a root, a switch, and a bunch of NVMe drives, right? Same kind of concept. It also added the concept of virtual hierarchies and what I'll call zoning, right? So I could have a host and kind of create a zone between these guys. So this host owns these two, these guys have zones. You have that in PCIe, right? A lot of vendors support this through vendor-specific features. The one interesting thing is that because we had this standardized fabric management, we actually created a kind of a standardized API that allows you to control this. Now, one of the downsides of this was that we can only have one T1, T2 device within a single hierarchy. So these two devices in host 1 could never be both .cache devices, right? The next thing we added was really the ability to take this device, break it up, and allow it to expose different parts to different hosts. So that's what you're kind of seeing here, right? Yeah, this guy owns all of this. Device 2 owns this part. Host 3 owns this part. Now the memory here is not shared. So you're really from a perspective of the backside memory, or if you're thinking an NVMe drive, right? The media behind it only gets exposed, a portion of the media only gets exposed to a single device at a time. So that's why they called it pooling. We added global persistent flash, or global persistent flush, and this was really a two-stage mechanism that allowed you to flush all the things. Because think about an environment where you potentially have what's shown here, where these devices are attached to this device, plus you have a little bit here, you have some off here that may be CXL on a different root port. Depending on what type of device it is, so let's say this is a caching device and it's caching data from here or it's caching data from up here, because they can cache this data too, right? Now it's owned by the host, but it can technically cache that data. So you needed the global persistent flush thing to basically tell everyone to flush everything, right? Because just because this guy's done flushing doesn't mean the rest of the system's done flushing. So that's kind of why they added the two-stage mechanism. Lastly, we added IDE, so basically link encryption on here. So CXL today does not support like flow-based or stream-based encryption that IDE on the PCIe side it does, and that's actually because of the FLIT. Initially because of the FLIT concept, and the concept that content in the FLIT as it transfers does not necessarily go to the same place. So when a FLIT comes in with a bunch of messages and stuff, those messages may not go to the same destinations. So if let's say I did 2 memory reads coming in, one may go here, one may go there, right? So you couldn't kind of encrypt on the link or do selective encryption at the moment. It probably will come, right? Because when that FLIT comes in here, and even in more granular terms, inside the slot today, the slot gets broken up, right? So as this FLIT comes in, it has 4 slots. And the 4 slots come in. Inside those 4 slots, you may actually have like memread commands that are going to be destined for 2 different things. So the switch is actually very complicated in CXL in that it has to take it in, it unpacks it, figures out where it's going to go, throws it onto different outbound queues, repackages it up, and sends it. So because of that, the initial uses of encryption were really at the link layer, right? Think kind of MACsec. I just encrypt everything. All right, so then 3.0 came along, and you see we're getting more and more complicated and trying to address more and more use cases. We bumped the speed up to Gen 6. We also changed kind of the FLIT structure from being a 68-byte FLIT to now we went to a more bigger 256-byte FLIT. And that added a lot of abilities to do other functions. Now, the only downside is a lot of the new functions that get added are not backwards compatible with the older 68-byte FLIT, just because the field doesn't exist in the old structure that's in the new structure. But what it did give us is the ability to do, I also should point out that in 2.0, because there's only one switch, it doesn't really matter. But in 2.0, the addressing, or let me say routing, was based on address, right? So when I had so inside like a .mem or a .mem read, there was basically an address of what I was trying to read. And the switch did the routing to know what device that went to based on that address in what virtual hierarchy it existed in. So everything was basically address routed. So there's no kind of concept that most fabrics don't use kind of addresses. They use more ports or MACs or something else to do the switching. So this is actually, but this is pretty, this is kind of how PCIe works. So it kind of followed that model. So in 3.0, right, we added the ability to do kind of have what I'll call an ISL, or have the ability to do multi-switches, and we added the ability to have more caching devices inside a virtual hierarchy. So now a virtual hierarchy can have more than one. And then we also added kind of a new kind of routing protocol called port-based routing. And so now instead of routing based on address, we're going to route based on ports. So this would be more traditional of a fabric, right? Or something like that, where you're actually routing from the end. You're routing based on these end-to-end things, kind of like Fiber Channel works, or Ethernet, somewhat Ethernet works, and those kind of things. And then on the other side, if you look at the MLD concept, which was we were pooling, we added the capability of doing sharing. And that really came from this concept of back and validate, which is now previously, right, the type 3 memory device was basically dumb, right? It was owned by the host. If you had the capability to do peer writes to it, that would be bad, right? Because you don't know if the host is caching that memory and everything. Luckily, you couldn't actually do that. If you tried to do it just based on PCIe and .mem, the traffic would actually go up to the host, resolve coherency, and come back down. I mean, that would happen automatically. But what back and validate allowed us to do is now the type 3 device becomes more intelligent and is now going to somewhat participate in the coherency, in terms of if a write comes in, he's gonna have to do a snoop request to the host or whoever and find out what the state of that cache line is. And if it's dirty, the host has to write it down before that write comes in. So what this then enabled was kind of the ability to do peer-to-peer. So it enabled peer-to-peer without having to go up to the root port and back down, right? Now, that only really applies for CXL devices. If you were doing like a PCIe wanted to write to .mem, it still would have to go up to the host as a PCIe TLP and then comes down as a write as a .mem, right? Because it's a different protocol, right? You don't read and write from type 3 memories as PCIe, right? It has its own protocol. It's .mem. I'm kind of going to skip that one in interest of time, but essentially we added protocols in reverse. The fabric capabilities really came along with the port-based routing and a lot of the new structures we're adding to allow you to do multipathing and all the other things. So really, what I want you to think is like 3.0 and 3.1, although they're added this, which is really key, the back and validate stuff, they're also driving down the fabric path. So we're putting in things that can now allow fabrics, right? So you can do multipathing and those kind of things. And then also they added this global GFAM. I'm not going to talk about it that much, but I think it has its histories from Gen Z, right? Because it's kind of more like a Gen Z device where it's a device out on the fabric and it's address based 0 to n instead of based on the host addresses. Like most devices, like even though this device is inside what I'll call the fabric, its HDM range for this device is in his host map. This S2 is in his host map. This S3 is in his host map. And this guy has to track, what address, who's coming to talk to me and from what host, and therefore what physical address I have to respond to for these different things, even though they're talking to the same backside media. Does that make sense? Because they're all in different host. They're all in different host, address spaces. I'm going to skip that one based on the time. So lastly, 3.1 kind of we started to do we started to build the kind of the fabric. So now with PBR, you're going to be able, I'll say that clearly, you're going to be able, assuming there's silicon and there's software and everything, that allow you to do really these kind of more mesh-oriented things. And that's what 3.1 was really about, was the fabric manager. We added trusted execution because apparently that's important now, so we added that. But it's only direct attach for now, and a lot of that has to do with actually the IDE stuff of not having selective flow IDE. So, and then additionally, the addition of the HDMDB, which is kind of the back and validate, the smart type 3 memory, adds a lot of complexities to trusted compute if you can have peer writes coming in, and and that changes the dynamics of the trusted compute environment. We have GIM, which was Global Integrated Memory, which was a concept of now I can use, actually, damn, I skipped the UIO slide, didn't I? You can use kind of UIO memory, or UIO, which is called unordered IO. It was a thing that PCIe added, and it allows, and it's a separate virtual channel, and allows you to kind of not follow the standard PCIe ordering rules and to get into like a device. And CXL, you can use that for peer-to-peer now. And then we added a bunch of RAS stuff, which I can cover. So this is kind of the GIM concept, and it's essentially allowing the concept of using UIO. You can kind of access this guy's memory. It is kind of the concept. UIO and PBR, you can do this kind of access. Is really kind of what it's about. So yeah, so that just shows you. All right, so now let's talk about kind of the CXL-ness. And how much time have I got?
Take as much as you need.
But I don't want to take too much. But so these are kind of the storage use cases. So when I started looking at kind of CXL and NVMe, right? Even internally, people were like, "Yeah, we're going to put NVMe on CXL," and I was doing kind of the CXL committee, and I would sit there and go, "Why? What's the value of putting an NVMe device with a CXL interface, right? You have a register interface, your block, you put your submission queue, you ring the doorbell, and it fetches the data. What is the value of CXL, right? And right, I say, yeah, you can do it. And if you ever build one, I'd be interested. I actually would be interested to test it just to see if it, if it's any better. But the reality to me is I expect it to be slower because of the overhead of doing the flits and everything else. So then I started thinking, well, CXL, NVMe has these other concepts like CMB, controller memory buffer or persistent memory region and things. And those, today are accessed via MMIO, and, what can go in there? Well, the spec is somewhat, gives some kind of ideas, right? You can put data in there, assuming that the bits are set to allow data. You can put queues in there. And so would putting that on a .mem range make sense, right? For this, yeah, maybe. I think so. But it really comes down to, a lot of people will say, oh yeah, it's cache coherent now. Well, not necessarily. It's cache coherent for one host, right? The one host who owns that drive, yeah, he can read drive to it. But wouldn't you want to have the ability to do peer? Which, okay, yes, you can, but now you need like an HDMDB device. So you need that smarter device that knows to, issue the backend validate. So yeah, okay, that's a possible. I don't know if it, if it really would provide you that. What I struggle with is I don't know if it really provides you that much, performance gain versus sourcing the data from somewhere else or writing it there, right? I mean, he talked a lot about, he's doing NVMe peer, right? Because he has a computational storage device. He can fetch via, so long as the PRP or the scatter-gather sources from there, it just does it, right? And you can do this too, right? You can do it even without NVMe, right? Because it will go up to the host, to the root port, and come back down and achieve the same thing. But I don't know if there's really going to be a performance gain in it. That's something I'd like to test if anyone actually builds these devices. Putting the queues there, I don't know if there's that much value. And the reason I say that is because you still have to synchronize the head pointer, the tail pointer. You still have to ring the doorbell, all those other things that still need kind of some of these posted writes. So you're still doing them. So is there that much value of having them, the ability to either fetch them from the host or write them, so do the post, or the .mem write versus actually during the, ring the doorbell, go fetch? I don't know the answer, or ring the head pointer, I should say, go fetch. Lastly, you could map them in as part of a namespace. This gets interesting if you have coherent access versus HDMDB. And you could probably map, and I think a lot of this you'll end up starting to see in Jason's presentation, I hope, around computational storage, because a lot of it, I think, maps to it. Oh, yeah, right here, and you'll see it. One of the interesting things I think may be useful is adding, if you're not going to do any kind of CXL-ness, adding UIO support, the NVMe drive, I think will be an interesting, right? Because that allows kind of sourcing and destinations of CXL.memory going through PCIe instead of having to going through, I guess it can be PCI, instead of having to go up to the root and back down. So this is, I think this would be one of the interesting ones if we're not, directly talking about computational storage use cases. And I don't know, maybe applicable to SDXI too, right? Yes. Now, the issue with UIO and with CXL is everything has to support UIO. So the T3 device has to support UIO. The switches have to support UIO. That's kind of the downside of UIO. And then we have a external storage. 2 minutes? Okay. So this is really, and this is more very conceptual. There's a lot of work that needs to be done on this. But today there are some big storage systems that kind of have this concept of, front controllers, and then they have a backside fabric, and then they have kind of the media devices, and these guys can all access any drive anywhere. I mean, there's a couple of them. Obviously, Dell sells one too. And generally, this is InfiniBand based. And so what this slide is really about is, could we replace InfiniBand or that other backside fabric with a CXL fabric? And the answer is kind of yes, but the answer is kind of it needs a lot of help in terms of I need UIO support, GIM support, PBR support, and there's a lot of aspects of HA and air handling that, in my opinion, are still kind of missing in CXL. And a lot of those have to do with what happens if the memory disappears? How do you do real multipathing? Do I map map the memory up to the twice? Who is gonna kind of hide? Or does the application see both memory and say, I only use this one, I only use this one. In case of a failure, then I do use this one. All those things need to be solved. So this one, I think, is very interesting, but it has a long way to go. And then lastly, I'll close with this slide, is composability, right? The one nice thing I think that with PBR, so now I can build these fancy meshes, and with this fabric manager, I now kind of have a standardized way of kind of starting to build this, where I can now, zone storage, networks storage, maybe a VF from this NIC and a NIC. I mean, you have endless kind of possibilities of how you can merge all this stuff together. And I think the enabler is really around the API. And there's work going on, I believe, in DMTF owns Redfish, right? Yeah, in DMTF to enable this API at a composability. Now this too, I think there's still more, some work to do, and I think like CXL 4 or 3 dot whatever coming in really is going to start focusing on quality of service, multipathing, and kind of air handling kind of within the fabric. And I think that's it.
Right, fantastic. Let's thank Kevin.
Yep.